Hello everyone, I'm going to talk about posits and how we can detect and debug numerical errors in posit applications using our approach. Posits are recently proposed by John Gustafson as a drop-in replacement for floating point. Posits can provide more accuracy and dynamic range for the same number of bits in comparison to floating point. Posit representation is designed to be hardware friendly. Now you write programs using posits and you encounter rounding errors. That's where PositDebug comes into the picture. In next few slides, I'm going to show you the approach behind PositDebug. We want to detect numerical errors with posit applications. We achieve this goal by doing shadow execution with real numbers. We want PositDebug to be usable with long-running applications. Careful design of metadata and compiler instrumentation helped us to achieve this goal by incurring lot less memory overheads in comparison to the other approaches. We want developers to identify the root cause of the numerical errors. To achieve this goal, we provide a directed acyclic graph of instructions to show the error propagation. The key contribution is how do we provide the DEG while maintaining constant amount of metadata with each memory location. Now let me show you how PositDebug works with an example. I will walk through this example later on, and details of the program are not important at this moment. PositDebug is based on LLVM compiler instrumentation. Posit values can either be resident in registers or in memory. That means we need to store metadata for variables in registers and variables in memory. For variables in register, we store metadata in the program stack. For variables in memory, we store metadata in shadow memory. Given the variable address, you can get the shadow address from which you can get the metadata. So what should we store in metadata for variables in registers? To perform shadow execution, we want to store the real value, which is used to compute the error by comparing real and posit value. There can be scenarios when shadow value is not available, or we have stale shadow value. We store posit value to reset the shadow value in such cases. To enable the user to diagnose the root cause of the numerical error, we store pointer to the metadata of both operands. Using these pointers, we can generate the DEG of instructions to do the root cause analysis. So the next question is, what should we store in metadata for variables in memory? The way program communicates with memory in LLVM IR is by storing the temporary to memory or loading the memory in temporary. All computations are done on temporaries. When we store the temporary to memory, we store the real value, posit value, and pointer to the temporary that has returned to the memory. The storing pointer to the temporary helps us to trace the provenance of numerical errors within the memory. But there is one problem. What if the stack frame is deallocated? Then pointer to the temporary and shadow memory metadata is a dangling pointer, and we need to check if it is safe to access this pointer. That means we need to ensure temporal safety of all pointers in the metadata space. We use the idea of lock and key from sets proposed by Nagarkate et al. Invariant maintained here is lock and key will match as long as pointer is safe to access. For more details, please check our paper. Now let me walk you through the example step by step. For variables in memory, we store metadata in shadow memory. For simplicity, I'm just showing real value, posit value, and the pointer to the temporary. For variables in register, we store metadata in the stack. The first thing I'm doing in this program is dereferencing a pointer ptr1. In shadow execution, I'm going to access the shadow memory associated with ptr1 and load the real and posit value in metadata space in fuse stack frame. To initialize the pointer to the metadata of each operands, I need to access T28, which is the pointer to the temporary in the stack frame. If it is valid, then we copy metadata associated with the operands of T28. Otherwise, we initialize operands metadata to null. In this case, it is invalid, and that's why pointer to the metadata of each operand is set to null. Similarly, we load metadata for B from PTR2 and metadata for C from PTR3. Now I'm calling root count function. For details on how do we handle function arguments and return, please see the paper. In the root count function, we are creating a new variable t1. In shadow execution, we create metadata for t1 in root count stack frame. We do real computation with real value of b and store it in t1's metadata. We store the posit value, computed value, and pointers to the t1's operands metadata, which is b in this case. We do the same thing for t2, t3, and t4. After computing t4, we notice that t4 has high rounding error, and t4's computed value is totally different than t4's real value. To diagnose the root cause of this error, we can traverse back following the pointers to the operands metadata and investigate how the error was propagated. The first thing we have noticed that subtraction operation at t4 has error of 62 bits. That is, all bits are wrong. From t4, we can access the t1 and t3's metadata and notice that both of the operands have the error of 43 bits. We recursively traverse each node and construct the entire DAG, which help us to do the root cause analysis. We figure out that T1 and T3 have error due to loss of precision, and it is magnified in T4 due to catastrophic cancellation. Now we return from the root count function, and root count stack frame is deallocated. At this point, T5 metadata is storing a dangling pointer to T1 and T3's metadata. By checking temporal safety metadata, we can know it is unsafe to access these pointers. Hence, at this point, we won't be able to produce the tag of instructions. The user has to put breakpoint just before this execution point to produce the tag. This design of storing the constant amount of metadata in program stack and following it to get the tag makes PositDebug scalable with long-running applications. Since PositDebug is based on compiler instrumentation, it can be used with interactive debuggers like GDB. Paper has a lot of other details, and due to lack of time, I'm not going to talk about it. If you are interested, please see the paper. Now I'm going to tell you how we evaluated PositDebug. In our experiments study, we evaluated the reliability, usability, and scalability of PositDebug. We performed experiments with a lot of micro benchmarks, some of them from Grind test suite. We also tested with large spec benchmarks and our own codic math library. We detected a lot of numerical errors in all these applications. PositDebug helped in detecting and diagnosing the root cause of the errors in codic math library. My group found PositDebug useful, and we improved the accuracy of Posit codic library by 10x. For performance experiments, we took applications from Polybench and Spec and ran them with PositDebug. We have used 256 bits of precision for shadow execution. Compared to the software version of Posit, PositDebug introduces 12x overhead on average. With the software version of Posits, PositDebug has low overheads, and we found it to be useful. Before I conclude, let me give you a quick overview of related work. Since posits are very new, there is not much support for detecting numerical errors with posits. There are two closest pieces of work in floating point domain, that is Grind and FPDebug. Both are Valgrind based dynamic instrumentation too. Our work is motivated by Grind, but we have different design goals. Grind's goal is to generate expressions so that they can be rewritten using Herbie. To achieve this goal, they do generalization, which requires to store metadata proportional to the dynamic trace of the program. In contrast, we store constant amount of metadata per memory location and provides DAG of instructions for debugging purposes. To conclude, posits is a new attractive representation for reals which provide tapered accuracy. PositDebug enables you to find numerical errors and debug them in Posit applications. The key idea is to keep the metadata constant to the amount of memory usage of the program. It provides backtracing in the active set of functions to produce the DAG for root cause analysis. We have shown the same ideas are applicable for floating point, and we believe both of these tools can help developers to debug and detect numerical errors effectively. Both of our tools, Posit and floating point version, are available online. Please try it out and give us feedback. Thank you for your attention.